Hi there, Mr. Sutton here, bringing you the AB Calculus 5-9 Extra Practice Number 2 solutions on FTC Graphical Analysis. For this problem, we're given a graph of f on the domain from -1 to 3, and we just want to know the integral from -1 to 3 of f of x dx. So basically just asking the area between the curve of f and the x-axis. One thing we do have to be careful about, though, is if an area is under the x-axis, it counts negative. So going from -1 to 3, it's really this whole graph here. We always want to check that. From -1 to 1, we have one particular shape, a trapezoid, but it's going to be negative area because it's underneath the x-axis. So to find this area, we're going to have a negative, and then using my trapezoid formula, we have the base is 2 plus 1 divided by 2 times a height of 2. So there's the trapezoid. And now we have to add to that this triangle here. This is going to be positive area. So that formula is going to be 1/2 base times height. So 1/2 base of 2 times a height of 2. And we're going to have to simplify this because we're matching answer choices. So for the trapezoid, these 2's are going to cancel. You've just got a negative fraction with a 3 and a 1 added on top. So that's -3 total. Over here, the 1/2 and the first 2 cancel. So that just leaves us with a 2. -3 plus 2 is -1, which gives us answer choice A. For this problem, we're given the g function, which is really just the integral from -1 to x of this craziness here. Now, we want to know on the interval from 0 to pi over 2, where does g attain a relative max? So to figure out relative maxes, we need to know where g prime is changing from positive to negative. Well, what is g prime? Since g is this integral function and we have an x in the upper limit of integration, g prime, using our fundamental theorem of calculus, is just going to be the integrand with this upper limit plugged in for t. So g prime is really just -1/2 plus cosine of x cubed plus 2 times x. And we just want to know where this changes from, it's a max, so positive to negative. This is a grapher problem, so let's graph that out and see what happens. So to make things a little bit easier, I've entered this function right here in my y equals as y1, and I'm going to go to window now, and for my x min and x max, I'm going to use the interval they gave me, 0 to pi over 2. So we've got 0, and we've got, let's see here, pi divided by 2. Let me do zoom 0, zoom fit, and let's see where this thing is crossing the x-axis. So we're changing positive to negative right there, and negative to positive over here. Now again, we wanted positive to negative. So it's this first critical value we want to look at. And if we do second trace and zeros, option 2, let's get a little bit to the left of that and press enter. There we go. A little bit to the right, press enter. Press enter one more time for good measure. And it comes out to about 0.471 and some change. So there was our graph. There was our x value. And because g prime is changing positive to negative at 0.471, that means g has a relative max at 0.471. So that's going to be choice A. On this one, we're given the graph of f on the interval from -2 to 2, and g is defined as the integral of f from 0 to x. We want to know which interval gives us a graph of g that is both decreasing and concave up. So if we want to know where g is decreasing and concave up, it would be awfully helpful if we knew where g prime was negative and increasing. So in order to figure out g prime, we're just going to take the derivative of this equation they gave us. Using the fundamental theorem, the derivative of this integral over here, we're just basically plugging x in for t. So this means that g prime of x is really none other than f of x. And now we're just trying to figure out then where f of x is negative and increasing. So this is going to be less than 0 and increasing if we look at the graph. Let's see, less than 0, that's everything to the right of the y-axis. And increasing at the same time, that's going to be from 1 to 2. This is the only interval where we're negative but also increasing. So because we're increasing and negative on that interval, it follows that g is decreasing and concave up on that same interval, which means we have to pick answer choice D. On this one, we're given the graph of g on the interval from 0 to 10, And we're also given f, which equals the integral from 4 to x squared of g of t dt. So we want the value of f prime of 3. Well, it would help if we knew what f prime of x was. Since f equals this integral function, f prime, we're just going to have to take the derivative of this integral. Now, since we have a variable in the upper limit of integration, using the fundamental theorem of calculus, we basically just plug this upper limit in for the dummy variable and use the chain rule if needed. So f prime can be written as g of x squared times, because we're taking a derivative and using the chain rule, we need the derivative of x squared, so that's going to be 2x that we're multiplying by. Now, if I want to figure out f prime of 3, I'm just going to plug 3 in for all these x's. So that's going to be, I'm just going to move this 2x out in front, so that's going to be 2 times 3 out in front, and we have g of 3 squared. Well, 2 times 3 is obviously 6. G of 3 squared, that's going to be g of 9. We do have a graph of g, so we can actually look this value up on the graph. If we look at 9 here, that falls right between these points that they gave you. So although they didn't give you the point explicitly, we clearly have a slope here. If we're going down 2 and over 2, this is a slope of -1. So if we take one step to the right, we're taking one step down, which means that this value has to be y equals 4 right there. So we've got 6 times 4, which is 24, giving us answer choice D. For this problem, we have this function f defined on an interval from 0 to 8, and the graph of f prime is shown right here. So we want to know at what x value we have the absolute min for f. So in general, we know the absolute min is going to happen either at one of the endpoints, 0 or 8, or at a critical value. Now, if you look at the critical values, because f prime is on the graph here, so you can see where f prime equals 0, we have two critical values, one at 4, which there's no sign change at all, so that's neither a min nor a max, so that's not really going to help. The other critical value, we're changing from positive to negative, so that's actually a local max, which there's no way that's going to be an absolute min. So really it comes down to the endpoints. Do we have a higher value at, or actually we want an absolute min, so do we have a lower value at 0 or at 8? Now the way to think about this, the graph of f is basically telling you how much area is under the curve of this f prime. So you want to have as little area as possible under this curve if you're trying to minimize the graph of f. How much, so what's likely to have less area? Starting back here before you've acquired all this positive area, or using the area all the way from 0 to 8? The key on this, the way I reason this out, is that although we can't figure out the exact area, from 0 to 6, the area is all positive, and more than offsets whatever negative area you picked up between 6 and 8. So for that reason, you're better off just taking whatever area you had at 0, and that's going to be your minimum value. So that ends up being answer choice A. For this free response problem, we're given the graph of f, which is differentiable, they're telling us, from -3 to 15. And they're also giving us a horizontal tangent line that they're saying exists at x equals 6. G is defined as 5 plus the integral of the f function from 6 to x on this interval here. So our first task is to figure out g of 6, g prime of 6, and g double prime of 6. Let's start with g of 6. So g of 6, here's the g function. We're just going to plug 6 in for x. No bells and whistles here. Now you might be thinking, well, how can I figure out this area? The key on this one, even though, geometrically it would be very tough to figure out any area on here, you have the same lower and upper limits of integration. You basically have an empty integral right here. You're not going anywhere. So this integral has a value of 0, so all that's left then is this 5 that was also part of the formula here. So g of 6 then just has to be 5. Now how about g prime of 6? Well, since g is all this stuff, g prime, this 5 is going to get zeroed out because it's a constant, and the derivative of this integral, since we have a variable in the upper limit of integration, it's just going to be f of x. You're just going to plug that in for your dummy variable using your fundamental theorem of calculus. So that means that g prime of 6 is really just f of 6. And what is f of 6? Well, f of 6 is just the value of the f graph at the x value 6. Looking up here, that's 3. All right. Well, if g prime of 6 is f of 6, it follows that g double prime of 6 is f single prime of 6, the slope of the f graph at x equals 6. Now again, in general, that's going to be tough to find on this graph because we have a whole lot of curving going on. However, at the x value 6, we're right up here, and they told us we have a horizontal tangent line at x equals 6. They spelled it out. That means the slope at 6 must be exactly 0. For this part of the problem, they want to know on what intervals is g decreasing with justification. So to figure this out, we'd like to know where g prime is negative. Well, the key on this is recognizing that g prime, and we did this on part A, but g prime of x is really, using our fundamental theorem here, just f of x. Again, this 5 is a constant and gets zeroed out, and a fundamental theorem, you're just plugging this upper limit into the dummy variable. So since g prime is really just f, and we're looking to see where g prime is negative, we're looking to see where f is negative. Well, here's a graph of f. We can observe on the graph that f is negative below the x-axis on the interval from -3 to 0, and also from 12 to 15. Since f is negative in these places, it follows that g is decreasing on those very same intervals. For this part of the problem, we want to know on what intervals the graph of g is concave down. So this means we want to know either where g double prime is negative, which is going to be kind of tricky to tell, or alternatively just where g prime is decreasing. So g prime, remember, that was just f of x. We saw that on parts A and B, but here it is again. And f of x, aka g prime, is decreasing, if you look at the graph here, on the interval from 6 all the way to 15. Therefore, we can say that g is concave down on the interval from 6 to 15. For this last part of the problem, they want the trapezoidal approximation of the integral from -3 to 15 of f of t dt, 6 subintervals, each of length 3. They didn't really, I guess they did need to tell you this because they didn't say 6 equal subintervals, but they're all going to be an equal length. So looking at our graph here, using our trapezoidal rule, we can say that this is approximately equal to the following. So in all of these, we're going to be doing a base 1 plus base 2 over 2 times the height kind of setup. So we're going to have 6 areas that we're finding here. First area, from -3 to 0, we've got the x value -1, or the y value -1, plus the y value 0, so base of -1 and 0, over 2, times our subinterval length of 3. It's going to be the height of 3, really. We've got some sideways trapezoids going on. Then for the next one, we've got 0 plus 1 over 2 times that height of 3. Then we have, let's see, 1 plus 3 over 2 times a height of 3. Next, we have 3 plus 1 over 2, height of 3. And then 1 plus 0 over 2 times 3. And this last one we're going to have, let's see here, 0 plus -1, or 0 minus 1 over 2 times 3. So we've got some symmetry going on here. You've actually already found the answer once you've written everything out with constants. But if you felt the need to simplify this and risk your score, I guess you could. You'll notice that these are all being multiplied by a 3 and divided by a 2. So if you wanted to, you could factor out a 3/2 from all of this. And then inside, we've just got, let's see, this is going to be -1 plus, this is +1 plus 4 plus 4 plus 1 minus 1. So the 1s are going to cancel. That's kind of nice. Add the 4s together, we've got an 8 inside there. So we have 3/2 times 8. 8 divided by 2 is 4, times 3 gives us a grand total of 12. But again, you could have stopped here. On this free response problem, we're given this graph of f, and we're told we've got 3 line segments and a quarter circle, which might come in handy to know. G is defined as the integral from 1 to x of f of t dt. Our first task is to find the average rate of change, AROC, of g from -5 to 5. So at some point we want to do g of 5 minus g of -5 all over 5 minus -5. So we're going to have to figure out what g of 5 and g of -5 are using this formula here. Let me start with g of -5. So plugging that in here, that's going to be basically the area from 1 to -5. Now, since we're going backwards, since we're going to a lower limit of integration, a lower number for our upper limit of integration, all the areas we compute while we do this are actually going to be opposite versions of the what they look like. So going backwards then, I'm going to start over here on the far left, over here at -5, and just work my way to +1. Again, realizing that everything I compute here has the opposite sign of what it looks like. So I've got a triangle here. Normally this would be negative area because it's under the x-axis, but again, since we're integrating backwards, that negative gets negated, so it actually becomes a positive area. And this is going to be 1/2 base of 3 times a height of 4. And we'll simplify a little bit later. Next we have this quarter circle. Again, this would be negative area normally under the x-axis, but backwards computed this becomes positive area. So this is going to be 1/4 pi r squared, so 1/4 pi times 2 squared. And then we have this little triangle here, same deal as these others, positive area because it's under the x-axis going backwards. So this is 1/2 times a base of 1 times a height of 2. All right. So it's not necessary to simplify this, but I'm going to anyway, just so I don't have to carry this around when I do my average rate of change. So let me do the non-pi stuff first. So here I've got 1/2 of 4, which is 2, times 3 is a 6. Over here, the 1/2 and the 2 cancel, so that's just a 1. 6 and 1 gives me 7 for my non-pi number. And now for the pi number here, we have 4 and 1/4 canceling, so this is just 7 plus pi when all is said and done. Now we go on to g of 5. That's the integral from 1 to 5, which is significantly more straightforward to compute because you really just have one shape here. It's a trapezoid, and you're going in the normal order. You're going from left to right, and it's positive area in general because it's above the x-axis. So this is just a straight-up positive trapezoid. We've got a base of 4 plus a base of 2 divided by 2, all over a height of 4. So this is going to be, let's see here, 6 over 2 is 3 times 4 is 12. So now, average rate of change on g from -5 to 5, again, that's going to be g of 5 minus g of -5, all over 5 minus -5. So this ends up being, let's see, 12 minus this stuff here. I'll put this in a parentheses. And you could leave it like this because you've got all constants, but if you really felt the need to simplify, this is going to be, let's see here, -7 minus pi. So that ends up being a 5 minus pi on top, and down below this is going to add up to 10. So this is as simplified as it's going to get. For this problem part, they want the instantaneous rate of change of g with respect to x at x equals 3, or say it doesn't exist. Basically, they want g prime. Now, here's the g function again. G prime of x in general, if you're taking the derivative of this integral with the x in the upper limit, you're just using your FTC, your fundamental theorem, and plugging in this upper limit for the dummy variable. So g prime of x really just turns out to be f of x, which means g prime of 3, which is what we're asking for here, is just f of 3. And f of 3, looking that up on the graph, because this is just the graph of f, that's just going to be this point up here. This is going to be 4. And that's it. For this part of the problem, we want to know on what open intervals is the graph concave up, the graph of g. So remember, so in general, g is going to be concave up where g prime is increasing. Now g prime, remember, going off of this using our fundamental theorem, g prime is really just f of x. So we want to know then where f of x is increasing, which is another thing we can just read directly off the graph. Looking at our graph of f, we're clearly increasing on the interval from -5 to -2, and also on the interval from 0 to 3. Therefore, g is concave up on those intervals. For this one, we want to find all x values in the interval from -5 to 5, in which g has a critical point, and then classify each of those as a local min, max, or neither. All right, so if I want to know where g has a critical point, I basically need to know where g prime is either 0 or undefined. Now keep in mind, based off of this formula for g and the fundamental theorem, g prime is just f of x. We've actually seen that on pretty much every part of this question except for part A, we didn't care. Parts B and C, though, we wrote this already. But I'm writing it again here just for good measure. So we want to know then where g prime, aka f of x, is either 0 or undefined. But if you look at the graph here, this is the graph of f. F is not undefined anywhere, so it really just comes down to where f of x equals 0. And there's two places that happens. One happens at x equals -2, and the other is over here at +1. So we need to figure out if each of these is a min, max, or neither. Let's look at -2 first. So in general, if I want to see if I have an extrema, we need some kind of sign change in g prime or f, one way or another. Since f, aka g prime, does not change signs at x equals -2, that means that x equals -2 is not a min or a max, neither of those. Next, at x equals 1, I notice g prime, which again is just f, is changing from negative to positive right there. This means that x equals 1, that is where g has a relative or a local min.